Student. Good morning to everybody. Now I'm going to cover the last part of the first chapter, nucleophilic substitution reaction. Now we are coming to the last part of this chapter. Now the last factor which we have to consider is the effect of solvent. Now you must know the whenever solvent effect is on, we are going to see on SN1 and SN1 mechanism, SN1 and SN2 mechanism. Now in this case, whenever we are considering the effect, then in that case, you must know there is a polar and a non-polar solvent. That means the polar solvent which contains the hydrogen, okay, and which are having a hydrogen and other electronegative atom. Like for example, in water, the oxygen having negative charge, hydrogen having positive charge. Thus the poles are developed. That is called as a polar solvent. And another is protic solvent, means which is polar and which contains a proton. That is called as a polar protic solvent. Now, whenever we are considering polar protic solvent, the polar protic solvent examples are the water, ammonia, in nitrogen also. Whenever we are considering, there is a different poles in hydrogen and nitrogen. Therefore, hydrogen having H positive charge in water, oxygen having negative charge. Like this, the poles are developed. Therefore, these are the polar solvent. They form the hydrogen bonding is possible with the help of in case of the polar solvent. See here example. Your starting material in case of SN1 mechanism is tertiary halide. That means general representation is Rx. Whenever the first state of SN1, as you know, the Rx bond breaks and R positive will get formed and X negative will get formed. Means formation of carbocation is there. This carbocation is formed R positive and X negative as a leaving group. Therefore, in first state, whenever the R positive gets formed, that is a carbocation in SN1 reaction, that is a rate determining state. Then R positive, well, if we are using the polar solvent like water, ammonia, if water or alcohol also, here I have shown ROH means alcohol, which is a polar and protic solvent. Therefore, R positive is there, that carbocation will form the bond with oxygen. As R is positive, oxygen is negative. Therefore, the bond is formed between R and O. Similarly, other molecule of alcohol binds with the R positive and this bond is called as a hydrogen bond. Therefore, the carbocation forms a hydrogen bond with R positive. Similarly, X negative is a leaving group which forms hydrogen bond with the alcohol H. This X is negative, hydrogen is positive. Therefore, this bond will form which is also a hydrogen bond. Therefore, in this case, whenever we are considering polar protic solvent, it can solvate both the ions, that means cation is R positive as well as the X negative, carbocation and leaving group. Both anions it will solvated through the hydrogen bonding. Therefore, due to this, the carbocation gets stabilized. Therefore, due to this polar protic solvent, the solvent polarity increases, then the carbocation will get stabilized through the hydrogen bonding. And thus, the polarity of solvent increases, the rate of SN1 also increases. Therefore, in SN1 reaction, if polarity of solvent increases and if we are using polar protic solvent, the rate of SN1 will increases due to the formation of the hydrogen bonding with the cation as well as the leaving group anion. Now, in case of the gaseous phase, what is happening? The SN1 reactions are uncommon in gaseous phase. Why? Because in gaseous phase, there is no solvent, there is no hydrogen bonding. Therefore, solvation of cation is not possible in gaseous state, and therefore SN1 mechanisms are always uncommon in gaseous phase. Okay, such kind of question they are asking for the reason. Okay, therefore you must know why SN1 reactions are uncommon in gaseous phase. Therefore, in short, the polar protic solvent, the rate of SN1 increases because the carbocation gets stabilized through the hydrogen bonding, the cation and anion gets solvated through hydrogen bonding. Now here we are going to consider SN2 mechanism. What is the effect of solvent on SN2? Effect of solvent on SN2, for that we have to consider the polar solvent and non-polar solvent also. associated solvent is non-polar, solvent is polar. Again, the polar solvent divided into two parts. Polar protic means polar and which contains a hydrogen also, and polar aprotic means which contains a which doesn't contain a hydrogen, that is called as a aprotic solvent. SN2 reactions prefers polar aprotic solvent. Therefore, in polar aprotic solvent, rate of SN2 will be more. Let us see how it takes place. For that, we have to consider the polar protic solvent first. See, in this polar protic solvent, this is the starting material. Whenever it will react with the nucleophile, here F negative, any halide is a nucleophile. Whenever it attacks from the backside, then the leaving group. As you know the mechanism of SN2, backside attack the nucleophile. This is F negative is here a nucleophile. But if your solvent is polar and protic, which contains hydrogen and which is polar, like alcohol, water, etc., what is happening? F is negative, nucleophile having the negative charge, and the polar protic solvent, hydrogen is there. Therefore, the F negative and hydrogen is H positive. Therefore, they form the hydrogen bond. Therefore, nucleophile will form the hydrogen bond with the polar protic solvent. And due to this, whenever polar protic solvent we are using like water or alcohol, it contains a hydrogen. Therefore, which can be solvated by the nucleophile. Nucleophile gets solvated through hydrogen bonding. Okay. Hence, the nucleophile is not free to attack. It is associated with the hydrogen bonding. It is not free to attack, and therefore rate of SN2 decreases. Polar protic solvent, which contains OH, NH, etc., they reduces the strength of the nucleophile because the nucleophile is not act as a nucleophile. It is bonded with hydrogen bonding. It is not free to attack. Therefore, it decreases the strength of the nucleophile. And due to polar protic solvent, thus rate of SN2 will decreases. Now, if the solvent is polar but aprotic, which doesn't contain a proton, such solvents examples are like CH3Cl, acetonitrile, then also dimethylformamide, means DMF. It is referred as a DMF. Dimethyl CH3N CH3 dimethylformamide. As formaldehyde, you know, C double bond OH aldehyde group is there. Therefore, dimethylformamide. Therefore, it is represented as a DMF. Then acetone. Acetone is a polar, but it doesn't contain a proton here. Therefore, these solvents are the polar, but they are aprotic solvent. Then in that case, some polar aprotic solvents I just told you, these are the examples: DMF, acetone, DNSO, dimethyl sulfoxide is also aprotic solvent. This solvent solvates the cation of the nucleophile Na positive, and suppose you are taking the nucleophile as a sodium azide, Na positive and N3 negative. Here N3 negative is a nucleophile. Therefore, in N3 negative, nucleophile is free, but it only solves the Na positive. It doesn't solve the N3 because proton is not there. Therefore, in polar aprotic solvent, they do not have the acidic proton, and therefore they cannot form the hydrogen bonding. Therefore, nucleophile is free to attack, and therefore in polar aprotic solvent, rate of SN2 increases. Therefore, in case of solvent effect, polar aprotic solvent, rate of SN2 will be more. While in case of polar protic solvent, the nucleophile is not free, it is bonded with the, or it solvates the polar solvents. Therefore, hydrogen bonding is formed with the polar solvent. Therefore, nucleophile F negative is not free to attack. Therefore, rate of SN2 in polar protic solvent decreases. While in polar aprotic solvent, the aprotic solvent doesn't contain proton.